Hmm. Hello, everyone, and welcome back to the next session. I'm here with Sam Bellen from Belgium, right, Sam?
From Belgium, correct? Yes.
Welcome. And you're going to introduce us to some magic, I think, cryptography. To me, as a developer, it's kind of like magic. You just use it and you trust that it works. But I hope you can shine some light on that for us.
Yeah, I hope that by the end of this talk, cryptography will seem a little bit less magic, even though we're going to stay with the basics.
Mhm.
But it is not all magic. There is some logic and there's some theory behind it as well.
And I guess you know what you talk about because you work at Auth0 and you're also a Google developer expert. So
Yep. Or I can pretend very well that I know what I'm talking about, but let's just assume that I know what I'm talking about. Yep.
I think you do. I don't think you need any further introduction. So the stage is yours. Keep the questions coming, everybody, and I will try to monitor the polls in the chat. And also, Sam put up a poll which you can answer as soon as you want to. So have a great talk.
Thank you very much. I hope my slides are on screen. If not, they should appear soonish. So
We can
yeah,
see
I
them.
created a little poll asking about who had heard about Jose before, because the title of this talk is No Way Jose, and Jose, it's not a Spanish name. Well, it's also a Spanish name, but it's also an acronym that stands for JSON Object Signing and Encryption. And usually when I talk about the Jose standard, the Jose specification, my first question is, who's ever heard about Jose? And I usually don't see many hands go up in the audience or the people I'm talking to. Well, I'm pretty sure that a big part of you have heard of some parts of the Jose specification. If I would ask about who has heard about JSON Web Tokens before, I think I would hear a lot or see a lot more hands go up. I would hear a lot more people saying, "Oh, I've heard about JSON Web Tokens before." And JSON Web Tokens are part of a group of specifications which are called the JSON Object Signing and Encryption, or Jose before. What's also part of this group, we're going to see by the end of this talk. But before I can talk about everything that is part of Jose, JSON Object Signing and Encryption, I'm going to do a little introduction on basic cryptography principles. Don't be scared when I say cryptography. The most difficult part about this talk is me pronouncing the word cryptography. You might hear me stumble when I say the word cryptography, even though I'm doing a good job at the moment. We're going to see the basics only. So let us get started. Let me quickly introduce myself. My name is Sam Bellen. I'm a developer advocate engineer at Auth0. And at Auth0, we try to make authentication as easy as possible so you can focus on building your application instead of building that stupid login and registering form that every application needs these days. As introduced, I'm also a Google developer expert. And if you want to find me on the internet, you can find me with the username Sambego on most of the social media websites. If you'd like to follow along with the slides on your own device, you can go to jose.sambego.tech. The slides are here. They will always be here. So if you'd like to see the slides after this presentation as well, they will also be available at this URL. And a little disclaimer, I might simplify certain things in order to try to explain them in an easier way, just because cryptography gets very complex very fast. I'm only going to stay on the top of this. I'm not going to do a deep dive into some of these concepts. We're just going to try to explain the basics of certain cryptography principles. And another disclaimer, please don't reinvent the wheel. When using cryptography, when doing something cryptographic, try to use proven solutions out there, proven libraries created by experts in the field who know what they're doing. Because even though I think I understand the basics, I'm still not an expert, and I always use reliable solutions out there that have been proven to be working by a big number of projects out there. So please don't reinvent the wheel. So what are we going to see in this presentation? We're going to have a look at hashing and keyed hashing. Then we're going to move on to signatures, digital signatures, encryption. And lastly, I'm going to talk about Jose because it's in the name of this presentation, No Way Jose. So let's get started with the first cryptographic principle I want to be talking about. A hashing algorithm is a mathematical algorithm that maps data of an arbitrary size to a bit string of a fixed size. And what does this actually mean? It means that no matter the size of the input of that hashing algorithm, the output is always going to be a fixed size depending on the algorithm you're using. So if you're using an algorithm with a 256-bit output is going to be that 256-bit output, no matter the input. So no matter if you put in one word, a whole book, a whole hard drive into that hashing algorithm, the output is always going to be the same size, the size defined by that algorithm. The initial data is often called a message. So the input of a hashing algorithm is called a message, and the outcome of that hashing function is often called a hash or a message digest. So when I say hash or a message digest in this part of the talk, I mean what comes out of a hashing algorithm. When I'm talking about the message or input, that's what you put into a hashing algorithm. And a hashing algorithm is a one-way algorithm. It's a one-way function, which means that you can never, or you should never be able to reverse the hash back to the original input. It's an input hashing output, and you can never revert that back to the original input. So if we look at a little example, we have our hashing algorithm in the middle. It's SHA-256 for this example. We have 3 different inputs: dog, doggo, and the quick brown fox jumps over the lazy dog. 3 different inputs, 3 different lengths. They're all 3 strings, but this could be any kind of input. Doesn't really matter. But the important part is there are 3 different lengths. They all go through the same hashing algorithm, and they all get 3 different hashes. But those 3 different hashes are all of the same size, being 256-bit for the SHA-256 algorithm. And it's also worth noting that the arrows go to the right. So the input goes through the algorithm, and you get hashes, and you should never be able to reverse them because a hash is non-reversible. Some of the more commonly used hashing algorithms are MD5, SHA, NDLM, and Landman. There's a few others, but SHA is the most commonly used one out of this list. If you've been on the internet for a long time, you might remember MD5, which we used back in the day to store passwords. We don't use it for that anymore because there are some issues with MD5 and collisions and stuff like that. But it is still useful for certain other use cases. So don't ignore MD5 altogether. But the most commonly used hashing algorithms these days are the SHA family. Okay, so we've seen a very brief overview of what hashing is. You always get the same size output. It's a non-reversible function, which means you should never be able to reverse a hash back to its input. So let's look at keyed hashes, which is everything that a hash is plus something extra on top. Keyed hashes lets you validate the integrity and authenticity of the content of a hash, which means that you're going to be able to validate the input. The hash belongs to the input that you expect it to be. And in order to compute a keyed hash, you need a secret key. A keyed hashing algorithm is based upon a secret key. We could also call this a password, something that is secret and should be kept secret only to whoever needs access to that secret key. So if we take the same example as before, but instead of just a regular SHA-256 algorithm, we have an HMAX SHA-256, which is a keyed hashing algorithm. It uses the same SHA-256 algorithm under the hood, but it adds that little secret box at the bottom as well. So we still have 3 inputs. We still have 3 hashes outputs, which are the same length, 256 bits in this case. But instead of having just one input, the dog, doggo, or the quick brown fox, etc., we have 2 inputs to this algorithm. We have the input, the actual thing we want to hash, and we have a secret. And if you combine those 2, the algorithm will give you a certain hash. Should I change that secret? The hash will also change for all 3 inputs. So this means that if we know the secret, we know which hash we can expect. So we can also validate that the input of that hashing algorithm has been the thing that we expect it to be, that it's authentic, that it's not been tampered with. So if we, for example, take this input, the quick brown fox, etc., and input it through this algorithm with the correct secret key, the correct password, the one we know, the one we expect it to be, we can see that the hash is one hash, and if we use a wrong secret, we get a different hash. And just because we know the secret, because we know the password, we can also know what hash to expect, because a hash is always going to be the same for the same input. So this means that with this secret key, super secret in this instance, you can validate the authenticity and integrity of the input, which is the quick brown fox. And some commonly used hashing algorithms are the HMAX SHA family. So it doesn't matter which output length or bit length you expect. HMAX SHA is the most commonly used keyed hashing algorithm out there today. And some example use cases for hashes and keyed hashes are storing passwords. I hope if there's one thing you take away from this talk, apart from cryptography is not that difficult, at least not on the surface level, is that you should never store passwords as plain text, and keyed hashes are often used to store passwords more securely in databases. You do other things like salting and stuff like that, but they're usually also always hashed. You can also use them for identifying files. You can use them for cache busting if you want to bust the cache of online files, and you append a little hash to every file name. You can use them for database indexes. And if you're interested in the blockchain technologies, they also use hashes quite heavily. Cool. We've seen hashes. We've seen keyed hashes. It's the first cryptographic principle I wanted to talk about. The second one is signing digital signatures. And digital signatures offer all properties of keyed hashes plus cryptographic non-repudiation. So everything we just saw about keyed hashes is also true for digital signatures plus cryptographic non-repudiation. Now, what does this mean? This non-repudiation refers to a situation where a statement author cannot successfully dispute its authorship or the validity of an associated contract. Thank you, Wikipedia. I don't think this helps me at all. But it's a very fancy term to say that a cryptographic non-repudiation can prove who created the signature. So whoever created a digital signature cannot dispute that they created it, because he can link that signature back to whoever created that. If that is a person, a service, whatever, you should always be able to prove who created that signature. And cryptographic non-repudiation enables other parties than the signer to check the signature's validity. With a keyed hash, you relied on both a secret key to do both the hash creation and the hash validation, which is not that ideal, because in theory, a secret is something you'd like to keep to yourself. You don't like to share with a lot of people, a lot of services out there. So it would be nice if there was another way for us to check the integrity and validity of a piece of data without having to share the same secret key that we use to both create a keyed hash and validate it. So that's where this cryptographic non-repudiation principle also steps in. And to do this with signatures, we use public key cryptography or asymmetric cryptography. They're the same thing, just different name for the same thing. And it means that they use a public and private key pair to create the signatures and to validate the signatures. So whoever wants to create a signature of a piece of data is going to use their private key, the key that they keep private to themselves, to create that signature. So they can send that signature to anybody that needs it. And then whoever wants to verify that the signature is valid, that the signature is valid for a piece of input, can use a private key that is linked to that, can use a public key, sorry, that's linked to that private key that has been used to create a signature to check the validity of that signature. And this is very important to note. We can share a public key with anybody because it's a public key, and anybody can use a public key to validate a signature created by a private key that is private to the person that used that key to generate that signature. And a signing algorithm is usually a collection of 3 algorithms, something that generates a public and private key pair, something that creates a signature, and something that uses a public key to verify that a signature is valid. So same kind of example as before. We have our input, the quick brown fox. We have our signing algorithm. In this case, it's an RSA-based signing algorithm, which does not only expect us to have given input, but also to use a private key to create a signature. So if we input the input and the private key into this algorithm, we get a signature. If then somebody else wants to validate the signature, they can use the exact input we used to generate that signature, together with the signature that we've generated in the previous step and the public key, run that through a verifying algorithm, and if the input is what we expect it to be, the algorithm will tell you, yep, it's valid. If it's not what we'd expect it to be, it will say, no, it's valid. But it's important to note that we use a public key for validation, and we use a private key for signing actual pieces of content. And the most commonly used public key cryptography approaches when signing are RSA, elliptic curve, and Edwards curve octet key pairs. So these are 3, let's call them families of algorithms for signing digital signatures out there in the world. And the first one, RSA keys, you have a few algorithms that implement an RSA key. The most commonly used ones are the RS and the PS family. And they're very fast for verification and very CPU friendly because they're relatively easy, let's call them. They're not that complex to compute, so they're quite fast to compute as well. They also have quite a good support, especially RS, because of they're quite easy to implement. So they're usually one of the first algorithms that libraries implement, and they've been around for quite some time. But they require relatively long keys, with a minimum of 56 bits is recommended to have a certain amount of security, which means longer keys also mean longer signatures. The next family is elliptic curve keys, where ES is the most commonly used algorithm that implements elliptic curve keys. And they require shorter keys for the same equivalent of the 2056-bit RSA strength that we talked about in the previous slides, which means they will have shorter signatures, but they're a bit more complex to compute, which means that they're a little slower to verify. It's a little slower to compute. And lastly, we have the Edwards curve octet keys. And they're a bit of best of both worlds in my book. They offer the best sounding performance, but because they're relatively new, they don't have the best support on libraries yet, even though that's catching on quite fast. And a lot of libraries are implementing or have already implemented Edward curve octet key support. So if they're available, I would recommend that you check them out and give them a try, because they do offer the best sounding performance out there today. And some example use cases for digital signatures are JSON Web Tokens. If you've used a JSON Web Token before, the payload and the header is always accompanied by a signature. This is either a keyed hash or a signature, but we'll go into the specifics of JSON Web Tokens later. And you can also use them for document signing and other things on the web. Cool. We've seen hashing and keyed hashing. We've seen encryption. There's only one cryptographic principle I'd like to be talking about before we move on to actual Jose, and that is encryption. And when encrypting data, we can not only ensure the integrity and authenticity of the data, like we could with keyed hashes and with signatures, but the data will stay secret for outsiders. This means that only people that are supposed to read the data to get access to that data should be able to get access to that data. You either need a private key, a secret key, or a password to read the data. This depends on which kind of algorithm you're using. The encrypted message is often called a cipher. So when I mention the word cipher, that's what comes out of an encryption algorithm, and that's what goes into a decryption algorithm. So it's the encrypted message itself. It's called a cipher. And like I said in a few slides back, you can either use a password, secret key, or private and public key pair to do encryption. And when using a symmetric encryption algorithm, you're going to use a password or secret key to do both encryption and decryption. And we often use them with when decrypting and encrypting big pieces of data, things like a file system, things like a database, things like a bunch of network traffic on our Wi-Fi. So when we're dealing with a big chunk of data, we're often going to use a symmetrical algorithm because they're a bit faster to compute. These are some examples. And the reason why they're a bit faster to compute is because they use a shared secret or password to do both encryption and decryption. So if we look at this example on screen right here, the quick brown fox jumps over the lazy dog. We can encrypt it using our shared secret super secret, and we can decrypt it using the same shared secret as well. And because we use this shared secret for both encryption and decryption, it's a bit faster to compute. And again, that's why we often use this kind of algorithms with big chunks of data. The other family next to symmetrical ones are the asymmetric encryption algorithms. And these use a public and private key pair again, like we saw with signatures, where instead of with a signature where you use a private key to create a signature and a public key to verify it, it's a bit of a mental shift, at least for myself, where you're going to use somebody's public key to encrypt data. So you're going to ask for somebody's public key. And again, it's a public key. It's something that you could be sharing with anybody you want. So you're going to ask for somebody's public key, use that public key to encrypt the data. And then when you get that data back, they can use their own matching private key, the key that matches with that public key they just shared, to decrypt the message. So instead of with signatures where you generate a signature with a private key and validate it with a public key, when talking about encryption, you're going to use a public key to encrypt the message, and you're going to use a private key to decrypt the message. For me, at least, that's a mental shift between the two. It's a mental reversement almost of the way of thinking. So if we look at the same example we saw a few slides back, we still have the same input, but we use a public key to encrypt the message, and we use a private key to decrypt that message. And where a hashing algorithm and a signature are non-reversible, just because you get a hash out of most of them or something hashed, an encryption algorithm is reversible because, of course, somebody that wants to consume that encrypted and decrypted message should be able to decrypt that message altogether. So this is a reversible algorithm. Some examples for the asymmetrical algorithms are TLS, VPN, and SSH. And these are some of the more commonly used algorithms. Note that they can be RSA, like with signatures based, or they can be Edwards curve based, like with signatures as well. So it doesn't matter if you're doing signatures or asymmetric encryption, those families of algorithms are all relying on the same basic principles for certain families like RSA, like Edwards curve, and so forth, like elliptic curve as well. I already mentioned this. I'm going to mention it again because it's a very important distinguishment. Why to use one over the others? Symmetrical algorithms are faster than asymmetrical ones, and we use them for big chunks of data most of the time because they are faster. So let's have a little look at RSA, a more detailed example. I'm going to use RSA because it's one of the more easier to explain examples out there, but there are many other algorithms out there as well that are even better, maybe. But we'll look at RSA for this example. And the first thing we need to do when working with RSA is generate a public and private key pairs, because RSA is asynchronous. So a small note, cryptography is usually based on some algorithms using large prime numbers. And is a million a large prime number or a large number? It's not a prime number. Is a billion a large number? No. When I'm talking about large numbers, this is a large number, where this would be a million, this would be a billion, and I have no idea how to call the actual number on screen, but I think it has about 150 digits. So when we talk about large prime numbers in cryptography, we mean numbers with hundreds of digits, if not more. So the first thing we need to do when generating a new public and private key pair is we're going to generate some secret numbers. We're going to generate two prime numbers, random prime numbers. In practice, they're going to be very large prime numbers. For this example, I chose 61 and 53 because it's just easier on the eyes. It's easier to understand this with small prime numbers. But do keep in mind that in practice, these are going to be very large prime numbers with hundreds of digits. So we generate two random prime numbers. And using those two prime numbers, we can also generate a lambda value, which is the least common multiplier of the first -1 and the second prime number -1. In this case, that gives us 780. And these are three secrets that we're only going to use to generate the public and private key pair. And after we've generated those two keys, we can forget about those numbers. We won't need them anymore. They can be put into the trash. But we will need them to generate the public key and the private key. And to generate the public key, we create the first thing, which is called the modulus, which is just the first prime number times the second, and the public exponent, usually used with the e value, which is a coprime of that lambda value we generated as a secret, in this case 17. And then the private key again has the modulus, the first prime times the second, and then it has the inverse of the modulus of the lambda of n as a private exponent, in this case 413. You don't have to do the math, I did it for you. But the important thing to know is that the public key and the private key are mathematically linked because they're both derived from those three secrets we generated in the first place. That first prime number, that second prime number, and that lambda value that is based on those two prime numbers as well. So the public key and private key are mathematically linked, and that's why it looks like magic, but it's basically just mathematics when you are dealing with these kind of keys. So once we have our public key, we can use that public key to encrypt some data. And the way you do this with RSA is you use this algorithm in the middle in the encryption box. So we have an input of 1, 2, 3, 4. I'm using numbers right here because in the end, it's a mathematical algorithm. And if we input the n and e value, which are our modulus and our public exponent value, together with that input into the RSA encryption algorithm, we get 2183. Now, it's worth noting that usually when dealing with encryption, we're not dealing with numbers. So we usually have to do quite a bit of data conversion. But under the hood, it's always going to be that mathematical algorithm that is going to do its work, and it's going to use the public key values, the modulus, and a public exponent to do the actual encryption. The same thing if you want to use a private key to decrypt that actual message that we just encrypted. The cipher that came out of our encryption algorithm before was 2183. So if we input this into the RSA decryption algorithm and we input the private key values, the modulus, and the private exponents, we should be able to get back to the original number 1234. And again, usually you don't work with numbers, but something else. So you might have to do some data conversion. But under the hood, it's always going to be that decryption algorithm, that mathematical algorithm that expects a few values and input a modulus and a private exponent from your private key. So to illustrate this a bit more, I have been hacking in the last few weekends on something that is this. It's a website, rsa.sambego.tech. It still has some bugs and it doesn't work in Safari, but if you're interested in reading a little bit more about how RSA works and seeing some of the numbers in action, you can go to this website and try to encrypt the message. So if we take the input of test, you can either see the encrypted message as the number that we dealt with under the hood. You see that's hex, ASCII, and so forth. But what you can see is that we generated two large prime numbers, the first one, the second one, and then the lambda value based on those two prime numbers. We generated the public key with our modulus and our public exponent, and the private key with our modulus and our private exponent. And as you can see in a more practical example, these are very large numbers. The lambda value is a lot of digits, so the same for modulus and private exponents, because they're based on those two large prime numbers. And by default, this website uses 48 bits, so 256 bytes. But we could also choose a larger bit size and then you'll see that the numbers are even bigger. These boxes keep on growing the larger we choose for bit size. So if you're interested in this, you can definitely check it out on rsa.sambego.tech. I'll share the link again in the end of this talk, but it should walk you through all of the mathematical things that happen with a basic RSA implementation, as I just explained in my slides as well. And if you'd like to do this in your terminal, I also have a little node script available on my GitHub where you can see multiple demonstrations. One for simple numbers, one for large numbers, and one that does a bit of data conversion. It's on my GitHub, but it explains the same thing, or it implements the same thing. Don't use this in production, it's just for demo purposes, but if you'd like to see some code that implements RSA as well in JavaScript and Node, go ahead and have a look at my GitHub as well. Okay, we're done with the introduction into cryptography. I still have quite a bit of time to explain Jose. But it's important to know that Jose is basically an implementation of signatures and encryption, or it uses signatures encryption to do certain things on the web. So Jose, JSON Object Signing and Encryption, that's what it stands for. And why JSON, you might ask? Well, JSON format is often used for serializing and transmitting structured data over a network connection, which basically means that we use it on the internet a lot. Some people still prefer XML. Some people might prefer other formats like YAML. But I think the most popular version, or the most popular format these days for structured data, especially on the internet, is JSON. And it has excellent support in most programming languages. It came from JavaScript, but I think most programming languages out there either have first-class support or have a library that deals with JSON. So we should be able to use JSON in most, if not all, programming languages out there. And Jose specifies a lot of JSON web somethings. I've mentioned JSON Web Tokens before, but we'll get started with JSON Web Keys. The first thing that we're going to see are JSON Web Keys, which is a JSON representation of public keys, which we can share on the internet as a piece of JSON. So if we look at an example, we see that it has an array with keys. This can be multiple keys. It can also be one, but it's always going to be an array that contains at least one public key. It tells us a bit of information like which algorithm we're using, RS-256. It tells us some more information like the key ID, but it also tells us the N and the E value. And if you've paid attention to the RSA demo explanation a few slides back, you might remember that the N value is the modulus, the first prime number times the second, and the E value is the public exponent that we calculated based on those secrets in our public key. So again, this JSON Web Key is a public key, and it contains the information we need in order to use it as a public key to encrypt data or to validate a signature. The next part of the HOSE specification are JSON Web Signatures. And if you've seen JSON Web Tokens before, this might seem familiar. It's a long random-ish looking string with 2 dots separating 3 parts, where the first part would be a base64 encoded JSON object, which we call the header. The second part, a base64 encoded JSON object, which we call the payload. And that last part is going to be the actual signature. So if we base64 decode that first part, we get a JSON object that tells us which algorithm to actually use to verify the signature of this JSON Web Signature. The payload, again, we can base64 decode that. And if we do so, anything that's valid JSON can be part of a JSON Web Signature. You can put some strings in here. You can put some Booleans, numbers, arrays, objects. As long as it's valid JSON, you can put this as the payload of a JSON Web Signature. And lastly, the signature. So we have to look into that header. We have to base64 decode that header, see which algorithm to use, then use a library that knows how to deal with that algorithm, and then input the header payload. And if you're using an HMAC SHA-256, which is basically a keyed hash, but most of the time this will be a secret. So this would be a public key you have to input instead of a secret. You will be able to validate the signature. You will be able to validate if something in that payload or header has changed or not, because the signature will only match the expected input, the expected payload and header. And lastly, we have JSON Web Encryption, and this is where it gets a little bit more complex. JSON Web Signatures had 3 parts: a header that told us basically which algorithm to use to verify the signature, the payload, so the actual content that has been signed, and the signature itself. JSON Web Encryption consists out of 5 parts, where the first part is still familiar. It's still going to be that HOSE header, still going to be a base64 encoded JSON object that will give us some more information about the actual JSON Web encrypted message. The second part is the JSON Web Encryption encrypted key. We have the initialization vector, which sometimes is an empty string. We have the ciphertext, which is the actual encrypted message in this JSON Web Encryption. And we have the authentication tag. And JSON Web Encryptions use 2 kinds of encryption. We already touched on this before. You have symmetric and asymmetric encryption. JSON Web Encryptions use both of them in combination to make it even more secure. So the content encryption key is usually encrypted with an asymmetrical algorithm. And the content encryption key is that second part of that very large string of those 5 parts. And that content encryption key is going to be encrypted in itself by using an asymmetrical algorithm, which means that we'll need a private key to decrypt that content encryption key. And the cipher, which is the actual encrypted message. And because we don't really know in advance how big a cipher or how big an input, how big a message it will be, it's encrypted using a symmetrical content encryption key. Remember that we spoke about this and that we said that we use symmetrical content encryption for big chunks of data. So the actual encrypted message in this JWE is encrypted using a symmetrical algorithm that uses that content encryption key that has been encrypted in the first place as well. So how do you work with these? The first thing, again, you look inside the header, and it tells us a bit about which algorithms to use to actually decrypt this JWE. So the first thing we need to do is decrypt the content encryption key, which we'll need to decrypt the actual cipher. So we look into our header. We see that we need to use the RSOAEP in this case algorithm. We take a library that knows how to deal with this, and we input the content encryption key, which is that second part of that string, together with our private key. And to know which private key to use, we'll also have a look inside of that header, and we see that the key ID that we need to use is the one that starts with NDZ and so forth. So if we input the right content encryption key, the right private key into this decryption algorithm, we should get the decrypted content encryption key. And once we've decrypted that content encryption key, we can use that key, that secret, to decrypt the actual ciphertext, to decrypt the actual encrypted message of this JWE. So again, we look into our header, we see that we have to use this algorithm, the A256 GCM, and we input our cipher, which is a third part of this long string, together with the decrypted content encryption key, the thing we just decrypted in the previous step. And we also input the initialization vector, which is sometimes an empty string, and the authentication tag. And if it all works out, we should be able to decrypt our actual JSON web encrypted message, to decrypt our actual ciphertext. So it's a bit more complicated. We first have to decrypt our content encryption key using an asymmetrical algorithm, which means we need to use our private key to decrypt this. But once we've done so, we can use this decrypted content encryption key to actually decrypt the ciphertext, the actual encrypted message we want to be working with. We want to get out of this JWE in the first place. And both JSON Web Signatures and JSON Web Encryption can be serialized as compact, the way I just showed you, where a signature would be a string consisting out of 3 parts, and a JWE would be one consisting out of 5 parts. But they're part of the Jose specification, JSON object sign-in encryption, so they can also be represented as a JSON object. And this would be a JSON representation of a JSON Web Signature. And again, we see the same kind of data in there. We have our payload, we have our signature with our header information and our actual signature. And this would be a JWE serialized as JSON. And again, it has the exact same information. It's just not base64 encoded anymore. It's not one big string. It's nicely represented as a JSON structure. But we see our initialization vector. We see our actual ciphertext, our authentication tag. Our header is in there, which tells us which algorithms to use, and so forth. So in JWS and in JWE, a JSON Web Signature and a JSON Web encrypted message can be serialized as a string and as a JSON object. And the reason why they can be serialized as a string is because they're often used as tokens. JSON Web Token is a specification part of Jose, but it basically implements either a JSON Web Token, a JSON Web Signature, or a JSON Web encryption serialized as a string. So JSON Web Token is always going to be serialized as a string, that 3 or 5 part string. A JWS and a JWE in itself can be both. Depending on your use case, you could either serialize it as a string or as a JSON object. And the most commonly, well, 99.9999% of the time when you use a JSON Web Token, it's going to be a JSON Web Signature, just because it's mostly overkill to encrypt those tokens. And most use cases for JSON Web Tokens should not contain any sensitive data anyway. So most of the time when we talk about JSON Web Tokens, we talk about a serialized JSON Web Signature serialized as a string. But if we look into the header, again, we see that we can find the algorithm to validate the signature, but we also see that the type has been added, which will be a JSON Web Token. So if we look at some example payloads of JSON Web Tokens, an access token is something that you use to get access to APIs with. So it's going to contain a bunch of information related to APIs. The issuer, which authorization server issued it, the subject, which user this token is for, audience, which API this is for, some scopes maybe, the issue date, expiry date. So anything in a JSON Web Token that is being used as an access token will be related to an API, while an ID token is more related to the identity of somebody to authenticate it. So the payload of a JSON Web Token that is used as an ID token will contain some more information about an actual user's identity, things like nickname or name or a picture, and again, an issue date, an expiry date, and so forth. So let's summarize, because I talked about a lot of different things, and I've seen this in the chat that there's a lot of information. I agree, I had a lot of information to share. So let's summarize and try to compress it all into a few sentences that you can take away from this talk. First off, hashing compresses and makes it virtually impossible to get to the real data. So when hashing something, you should never be able to reverse that hash back to the original input. It has always the same, it's always going to have the length defined by the algorithm that you're using. So if you use SHA-256, it's going to be 256 bits long. Keyed hashes do everything that a hash can do, plus it can protect the integrity of the data, just because we also add a secret key into the mix of hashes. Digital signatures allow third parties to verify the validity and origin of data. Well, with a keyed hash, you would have to share a shared secret. With digital signatures, you won't have to share that shared secret because you would use a public key to validate the validity of that signature, and you would use a private key, which you keep secret to yourself, to generate those signatures. So they're better suited to share with third parties because a public key is shareable with anybody you'd like to. Encryption allows only authorized people to read the data. Only people that know how to decrypt an encrypted message should be able to get to the original data. And Jose is a set of standards based on JSON that helps us with signatures and encryption on the web. Again, you can serialize them as a string, 3 parts for signatures, 5 parts for encryption. They're much shorter, and that's why we use them for tokens most of the time. Well, JSON Web Tokens are always going to be serialized as strings because we often send them with each request, so we try to get them as small as possible. That's why we often serialize them as a string. But you can also serialize them as a JSON structure, and then there's a predefined structure for both JSON Web signatures, keys, and encrypted messages. These slides are available and will always be available at jose.sambigo.tech. They might change a little bit because my slides are always evolving, but the general information will always be part of these slides. If you want to learn more about JSON Web Tokens, jwt.io is a website that I maintain for Auth0, which has a bunch of information about JSON Web Tokens. It gives you a nice debugger, and there's a bunch of libraries that help you deal with JSON Web Tokens, so you don't have to implement it yourself. The RSA demo that I showed in the middle of this talk is available at rsa.sambigo.tech. It's still a work in progress, so please don't send me angry tweets like, hey, this is broken. I know there's still some work to do, but I just wanted to put it out there because it might be interesting to some people. If you're interested to see how SHA-256 work, it's a very complicated algorithm. It's a hashing algorithm. You can go to SHA-256algorithm.com. I didn't make this. Whoever made this is a genius. I am not, but it's definitely worth checking out. Being said, thank you very much. And if there's any questions, I'll be happy to try and answer them now.
Thank you very much, Sam. Lovely presentation. You got a lot of positive feedback. I guess you saw that.
I'm keeping an eye on it. Yeah, I saw some messages. Thank you, everybody, for the positive feedback. If there's questions, let me know.
Super structured and nicely built up, knowledge-wise. Great. Let's see. No questions yet.
Okay. That means I either was very clear.
We have one. We have one.
Okay.
It's from Marius, and he or she is asking, what could be a use case for JWE or JWT?
So a JWE is basically just an encrypted message, and the JWE specification just specifies a structured way of including everything you need to do to have to work with an encrypted message. So if you want to send an encrypted message over the internet to somebody else, you could use a JWE. Usually you're not going to do this as a person, but one application or service is going to do this to another application or service. So if you're dealing with encrypted messages, encryption and decryption on the web, JWE is always going to be a good use case, because in the end, it's either a bunch of JSON or a string that you can then decode to be a bunch of JSON as well. JSON Web Tokens are the most common use cases are either ID tokens, which is an artifact that you get when logging in when using OpenID Connect, which most of us use on a daily basis, if we know it or not, or as an access token. And JSON Web Token access token is something that you would attach to every request that we would like to make to an API that needs to be authenticated or authorized. I hope that answers the question.
I guess
and JSON Web Signatures, again, can be used in any scenario you can think of where you want to sign a piece of data on the web. And just because it's either a string or a piece of JSON, it's nice to work with, especially in an internet environment.
Great. Thank you for a wonderful presentation. Absolutely marvelous. Thank you very much.
You're welcome. Thank you, everybody, for joining me.
Yeah, have a great rest of the day. And for the rest of you guys, I hope you see you in the upcoming sessions in like 5 minutes or something. So bye. Thank you very much.